Hello and a warm welcome to my YouTube channel. Let's get on with some organic chemistry. This is my favourite topic area. I'm going to promise to use my neatest handwriting, and I wonder why students are not like this. Students are often like this. So let's go from here to here by the end of this tutorial. So first of all, organic chemistry is to do with the chemistry of carbon and hydrogen. To a lesser extent, we can also have oxygen. Even lesser extent, we can have sulfur and nitrogen. Of course, all of the symbols of these elements you know, right? C, H, O, S, and N. Element symbols. And the biggest, most important symbol in all of those is carbon. You are a carbon-based life form. I hope you are feeling happy today. So, dear carbon-based life forms, where do we begin? We begin at the beginning. And where does crude oil come from? Well, your examiners want you to say dead sea creatures. Things that used to be swimming around in the ocean, dead sea creatures. They died. Oh, sorry for sea creatures. They fell to the bottom of the ocean, on the seabed, and they were compressed over millions of years. In the absence of, well, in the absence of you and I, but in the absence of oxygen. Key things you need to say to get the marks: dead sea creatures, millions of years, absence of oxygen. And it's difficult to visualize this because, well, here's you and your mates, and you're on a hill, and at the bottom of the hill there is the ocean. And the seabed kind of levels out a bit. It might be a trough or a mountain or whatever happens. The surface of the water could be choppy, could be wavy, could be flat. It doesn't matter. Where is the crude oil? This black sludgy stuff you often see on the news that's responsible for killing all the sea creatures that we're alive. So along comes here's a ship. This is why I don't teach art. Here's a ship, comes along, got a big drill, drills through the rock of the seabed and accesses this big cavern of what we call crude oil. Now, crude oil is a mixture. It's a mixture of hydrocarbons. Okay, hydrocarbons, that's our second mark scheme point. Hydrocarbons contain, as the name suggests, carbon and hydrogen. Is that enough to get a mark on your paper? No, because the iGCSE want you to say hydrocarbons contain carbon and hydrogen only. And if you don't put only at the bottom of your definition of what a hydrocarbon is, you get no marks. Make sure you use the word only. Okay, so our ship has come along. We dug up our crude oil here. The crude oil is now on the ship, and the ship sails back to shore to a processing plant or a chemical factory. Okay, so dead sea creatures, millions of years, absence of oxygen, crude oil pumped up, assuming the ship doesn't encounter a storm or a rock or a collision and kills more sea creatures. Then it gets to the processing facility where the hydrocarbons containing carbon and hydrogen only are separated. So how do we separate crude oil into its component parts? Well, each part is a different molecular weight, molecular size, or chain length, or however you want to put it. So here comes along my ship. That's a sail here, by the way, ship, and it's got all its crude oil in the bottom, and it's just discharged, and it's discharged into a fractional distillation column. Fractional distillation works on the basis of each fraction has a different, you got it, boiling point. At the bottom of here, it's hot. I always teach my students, big, hot bottom. Seems to stick in the brain, don't know why. Why is it big? Because this is where the big molecules will condense. That means at the top we're going to get the small molecules. Here's the big ones. In the middle we get the medium molecules. We'll get some names on in a second. Big hot bottom, so there's normally a fire or a heating element at the bottom in here. The crude oil is pumped into here, and it evaporates 1, 2, 3, 4, 5, and then at different levels it will condense at different temperatures. So different fractions will condense at different temperatures. So fractions will condense at different temperatures. What do we get at the bottom? Well, we're going to get, coming off the bottom, and everyone remembers this, right? Bitumen. Bitumen is used in road building. It's the tarmac that your car or your parents' car drives over. Above the bitumen, we're going to get something called fuel oil. So this could be used to power ships, sometimes called dog diesel. It burns very uncleanly. It's a dirty burn. You get lots of carbon soot, which comes off as well. Next up, we're going to get some diesel, obviously used in cars and lorries, transportation. Next up, we're going to get some kerosene, used for heating, used for lamps. It could be used in further processing. Next up, we're going to get some petrol. If you don't know what petrol is used for, hit the books down. And then coming off at the top are gases, sometimes called refinery gases. So fractions are separated at different temperatures on the basis of their boiling points. Fractions condense at different temperatures because they have different boiling points. They have different boiling points because they have different molecular weights. Different boiling points because of different molecular weights. The bigger the molecule, the higher the boiling point. The smaller the molecule, the lower the boiling point. So we are interested in making money. We are. At the top of the column, I can get lots of dollars. I can get Japanese yen. I can get English pounds. I think they still exist. I can get euros. They definitely exist. For this one, this one, this one, kind of there, my immediate convert to cash factor excuse me, is diminished. But we get as much of these as we do of these. So these things at the bottom we need to send to further refining, which we call cracking. These ones we can sell, make some crazy dollars, and these ones at the top, the refinery gases, are separated further into, these are the alkanes. So at the top of our column we get our alkanes, which come off as refinery gases, these things here. Petrol we can put in the car, kerosene we can put in the lamp, diesel we can put in the cars and the lorries. So we are going to refine the bottom bits and the top bits. So the first thing we're going to start with are the top bits. The top bits are from the refinery gases. Refinery gases. In the refinery gases are these wonderful things called the alkanes. Okay, general formula of an alkane is CnH2n plus 2. So if there were 10 carbons, there would be 22 hydrogens. If there were 100 carbons, there would be 202 hydrogens. If there were 4 carbons, there would be 10 hydrogens. And finally, if there were 6 carbons, there would be 14 hydrogens. So double the amount of carbon, add 2, and you get the number of hydrogen for an alkane. An alkane is described as saturated. That means there's no room for any more hydrogen. They all have single bonds. So it's all going to be C to H to H to H. There's none of that C double bond C to H nonsense, which we will get to shortly. So these are alkanes. Bonus prize for guessing that these are alkenes. Don't get clever and think you're going to do a funny little AE thing in the middle here, and your examiner won't notice and will just give you the mark. They do care, we do care, that this is an E and this is an A, and it should be very prominent about which one it is. So I'm Mr. Midgley, and what I teach my students is the first 4 alkanes, which you need to know for success at iGCSE Coordinated Science, are methane, ethane, propane, and a butane. In terms of number of carbons, that's 1, that's 2, that's 3, and that's 4. After that, if you're interested, it just goes on, just like shapes, so pentane and hexane. Why's my pen not working? You get the idea. So methane has 1 carbon. There we go. Ethane has 2, propane has 3, and butane has 4. Now they're kind of undressed. So what do we need to do? We need to be able to count to the valency of carbon, which is 4, always 4, never less and never more. So all I do is count to 4. 1, 2, 3, 4. Put a little H at the end of there. I'm going to struggle on that because I've not left myself enough space. Let's do that one again. C to C. And here, so 1, 2, 3, 4. That's the 1. 1, 2, 3, 4. Drawing the hydrogen. It's a bit tedious, but it gets me marks on my iGCSE, so who am I to complain? Propane was 1, 2, 3. Now just count to 4. 1, 2, 3, 4. 1, 2, 3, 4. That's left and right. 1, 2, 3, 4. Right in the hydrogen. All you have to do is count to 4. Let's have a rub that one out as well, haven't I? Okay, so butane was 1, 2, 3, 4. Count to 4 around each carbon. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right in the hydrogen. Hum a song to yourself while I'm doing that. Jolly good. So those are the first 4 alkanes. We'll recognise them because they're all single bonds between each of the carbon atoms. And what are they used for? Well, they're used as fuels. These are fuels. They can be used for further processing. There are some reactions that they can do. If you want to do A-level, IB or AP chemistry, you'll find out all about what they do. But mostly these alkanes are used for burning, combustion, or for getting energy. So combustion reactions of alkanes. You will often be asked to balance an equation, so let's start nice and easy. CH4 plus O2. If it is complete combustion, this is complete combustion. That means there's lots of oxygen, or in excess, as we say. We only make 2 products, CO2, global warming, and water vapor, also involved in global warming. CH4 is a gas, oxygen's a gas, CO2 is a gas. This is going to be gaseous as well because we're burning. It's going to be really hot. This is exothermic, okay, because it's a combustion reaction. Now to balance this equation, you do it in the order of CHO. Cho means a lot in Japanese. Cho genki means you're very happy. Carbons on the left-hand side, so left and right, or we could say reactants and products. So on the left-hand side, so everything this way, there is 1 carbon. And here on the right-hand side, everything this way, there is 1 carbon. So carbon's happy. Here there are 4 hydrogens, here there are 2 hydrogens, 4 and 2. So how we're going to get around that? We're going to have 2 lots of water, because now we've got 2 times 2, which is 4. So hydrogen is happy. Now the oxygen, there are 2 oxygen here and 2 oxygen here, so we've got 4 oxygen on the right hand side, and we have 2 on the left hand side. Simple thing to do, put a 2 at the beginning, now that is 4, and oxygen is happy. As a rule of thumb, always leave the atom or molecule which is on its own when you're balancing an equation until last, because that's the easiest thing to balance. It's much more much more difficult to balance a more complicated molecule like this. So let's try the next alkane. So it's methane. So ethane was C2. How many hydrogen? Double add 2, 6, plus O2 makes CO2 plus H2O. So we're going to do our CHO, CHO, and 2 carbons, 1 carbon, so 2, 1, so we need to have 2 of those. Now carbon is happy. Hydrogen 6, hydrogen 2, 2, so we need to have 3 of those, so that's now 6, so hydrogen is happy. Oxygen 2 times 2 is 4, plus 3 times 1, so there are 7 oxygens on the right hand side, and there are 2 here. And now you're thinking, OMG, MgO, what we're going to do? Well, you could put 3.5 or 2, but your exam board don't like that. So what you need to do is to multiply out the fraction, and to do that we need to times everything by 2, times the whole equation by 2. So what colour should we use? Let's use green. So that means I need to, instead of 1, I've got 2 of these. Instead of 3.5, I've now got 7 of these. Instead of 2, I've now got 4 of these. And instead of 3, I now have 6 of these. Does that balance? Of course it does. Give me 3 marks. Thank you. The next alkane, C3, double add 2, 8 plus O2 makes CO2 plus H2O, because it's complete combustion. Let's do that same CHO, CHO. Carbon's 3, carbon's 1, so I need to times that by 3. Carbon is good. Hydrogen's 8, hydrogen's 2, so I need to times that by 4. So now we've got 8 and 8, that's good. Oxygen, we've got 3 times 2 is 6, plus 4, so we've got 10 oxygen. Only 2 here, so it's 5, so it's 10. Add 10, and that is balanced beautifully. Thank you, propane. Okay. Let's do butane just for completeness. So butane is BC4, double add 2 is 10, plus O2 goes to CO2 plus H2O. Let's balance CHO, CHO. So carbon is 4, 1, so that's 4, done. Hydrogen is 10, 2, so it's 5, 10 and 10, done. Oxygen is 4 times 2, which is 8, plus 5 is 13. Oxygens on this side, can you see that? And there are 2 there. So we're back with the same problem we had with ethane. We've got a fraction. So we're going to do the same thing again. We're going to double the whole thing together. So we just rub out. That was 1. It is now 2. This was 6.5. It's now 13. This was 8. Yeah, sorry, it's 4. Now it's 8. And this was 5. Thank you. And now it's 10. Balanced beautifully. Great stuff. So the first 4 alkanes are methane, ethane, propane, and butane. 1 carbon, 2 carbon, 3 carbon, 4. Then just do your CnH2n plus 2. You could put my elephant, to remember it, parks backwards. or my students' current favourite is Midgley, that's me, eats pink biscuits. Whatever floats your boat, let it float. Okay, so those are the alkanes. We shall go on to the alkenes, which are much more useful. The general formula for an alkene is CnH2n. So if it's C10, it's H20. C2, it's H4, C3, H6, C100, H200. Easy, right? Now the alkanes, we burnt them, we combusted them. The alkenes, we don't do that because they're much more useful. Alkenes, let's start with a simple one, named in the same way. This is the first alkene, and this is ethene. We can also have 1, 2, 3 double bonds, still count to 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Write the hydrogen in. 3 carbons. Midgley eats pink, so it's P. So this one is pro. Again, make sure your E is really prominent, not an A, propene. And the next one, of course, is 1, 2, 3, 4. Put the double bond here, or you can put it here. We really don't care. As long as it has 1, that is fine. So we're going to just have 1, 2, 3, 4. Again, count to 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Write in your hydrogen. C4H8, count them up, is going to be butene. Okay. Why are alkenes so useful? Well, they do 4 characteristic reactions that you need to know for success at iGCSE Chemistry for the double award, Coordinated Science. The first reaction, let's do this one, is with steam. Steam is gaseous or gaseous water. And the thing that we make is the thing which you should not drink. It is ethanol, which is the alcohol present in beer and wine and spirits and all those other nasty things. But if it asks you the use of ethanol on the mark scheme, it doesn't say to get people drunk. No, it says as a fuel. So this is a fuel used a lot in South America to fuel cars. Okay, so it's ethene plus steam is ethanol. Ethene plus hydrogen with a nickel catalyst is going to hydrogenate it, or add hydrogen. So we're going to go from ethene to ethane. In all honesty, only a fool would do this, because adding hydrogen to this molecule makes it less useful to make the alkane. But if you have a really long molecule of polyunsaturated, this is the alkenes, which are unsaturated. Remember that alkanes were saturated. Unsaturated, that means there's room for more hydrogen. Then we can do this in an unsaturated oil. So this is the use for this is making saturated fats. So that's changing olive oil to olive oil spread. Okay, so making margarine basically. The other reaction we can do is we can test using bromine water. If bromine with an alkane, it would stay reddy brown. It's reddy brown as it is in the bottle. But as you add it to a double bond, it will go from reddy brown and it will decolorize. I'll use the American spelling. Decolorize. Because what's happened is the double bond has broken and bromine has added across the double bond to make 1,2-dibromoethane. For double award science, you don't need to know that. If you want to do the IB, AP, A-level, then you will be taught about this as electrophilic addition. But let's leave that for now. So what's the other reaction? We've got hydrogen, we've got bromine, we've got water. The other reaction is where we take millions and millions. So N is a really big number. Take millions and millions of these. We heat and a catalyst, and all the double bonds open up and bond to their neighbouring ethene. Let's use the word monomers. So this can be a monomer. I'll do a separate video on plastics and polymerization separate to this, which is a basic introduction to organic chemistry. So this, you see my hands are getting tired. The polymer formed is going to go off into space, probably in both directions, for n number of repeat units. Okay, so this bond here is going to break, it's going to be lost, it's going to bond with a neighbouring monomer, and it's going to extend into space, which is what we've made here. We're chemists, we're intelligent people, and we get bored pretty quickly. So what we do is we find the smallest subunit that represents the whole chain, that if we were to copy that again there and again there and again two there and again two there, this describes the whole chain if we write a little n at the bottom. So we'll do a longer video on that, as I said. So alkenes are really useful. Let's put the double bond back in. Alkenes are really useful because they can be used to make ethanol, which is a fuel. They can be hydrogenated to make saturated fats. You can test for an alkene or an alkane using bromine water. Bromine water stays reddy brown with an alkane. It will decolorize with an alkene. Or you can begin to think about using it as a monomer to make a polymer. So alkenes are vastly more useful than the counterpart alkanes, which we basically burn. Okay, so I'm going to leave it there. That was a gentle introduction to organic chemistry. We went from crude oil, we got it to the fractional distillation column. We did the alkanes. Midgley eats pink biscuits, my elephant parks backwards, many eat purple bananas. Just remember methane, ethane, propane, butane, general formula CnH2n plus 2. Combustion reactions, balancing equations, CHO. The alkenes, where it's CnH2n, and the four main reactions that you need to know. Okay, we'll leave it there.